All right, welcome everybody to this episode of It's Always Sunny at VCF, in which the gang tries to explain a broad, overly complicated topic in 45 minutes. We are going to be talking about reverse engineering, specifically retrocomputing hardware. We'll touch a tiny little bit on software, though that will more or less probably wind up being something more akin to firmware than actual software. So what is reverse engineering? I am sure that is a term that most are familiar with, especially if you were in this hobby. Reverse engineering is really just taking something apart and figuring out how it works. Ideally, you're able to put it back together again. When I turned 3, my mom's mom, for my birthday, bought me a box fan to take apart because I took apart everything in our house and I never put it back together. And I enjoyed it. I'm pretty sure eventually I did put that box fan back together, but I wanted to know how it worked. And that was a really sort of pivotal moment, a long moment of taking things apart on what I would eventually become in my later years, which is someone that works on trying to take apart retrocomputing hardware, figuring out how it works, making another of it that hopefully works, and being able to put the original back in ideally a non-destructive fashion. Reverse engineering is not strictly a hardware thing. It can be a software thing as well. You can reverse engineer things like peripherals, computer hardware itself, chips. That can also apply to processes, things like how something is made. Coca-Cola, probably one of the more important food things in the 20th and 21st century as far as money is concerned. There is no telling how many people have tried to figure out how to make it, because if you can figure out how to do something like knock off Coca-Cola, ideally you can make the same kind of money. You can't. It's more complicated than that. So let's talk about what reverse engineering is not. It is not magic. There are no silver bullets. It is not like you can just open something up and look at it and close the box and you know how it works. There's an asterisk there because, and I'll dovetail for just a moment and explain what some actual silver bullets are. Whether or not you would consider them ethical, there are certainly places that exist that you can have hardware shipped to, that those firms' entire existence is basically to take things apart, figure them out, put them back together, and deliver a finished product to you. Again, whether or not that is ethical is kind of beyond the scope of this, but if you have the time and the money and the resources, and you are a large corporation that wants to pursue something like that, that is a bit of a magic bullet. But for what we do, it's never that simple. It is not fast. There is, as we'll see in the next slide, there's a lot of work involved. It is usually a slow, tedious process of taking individual things off of a circuit board if you're working with hardware, or if you're going to be non-destructive, you're going to be using something like a multimeter, and you're going to be toning out each connection on that circuit board. And if you have something as complicated as, can you pull the CPU card if you've got one? Yeah. So if you have something as complicated as this, which is a Lisa CPU card, there are, I believe, 1,800 solder pads on this circuit board, which means each one of those bridges to something else. So at a minimum, there's probably around 900 traces that you would have to tone out. You cannot do that in an afternoon. You probably couldn't do that in a week if you wanted to maintain your sanity. But you can do it, and there's plenty of people that do. Alternatively, you can just take everything off a board, and Alex is going to talk a little bit about that here in a minute, and take an image of the board and go over it optically and figure out where everything needs to connect to. It's much more destructive. It's also time intensive, but it does work, and it's very accurate. It's almost never cheap. Part of that has to do with the investment in tools that go into doing some of the higher level stuff that Alex is going to be talking about. It can be cheap. If you're working on something that is as simple as like a 555 timer and a capacitor and a potentiometer and an LED, and you want to figure out why that light blinks at different speeds when you turn that potentiometer one way or the other, that's a fairly cheap thing to start with, and is actually probably a decent thing to start with, because you can go look at the documentation for how all of those parts work and grasp, come to an understanding of how they're supposed to fit together. And so yes, there are certainly cheap things that you can start with, but as you get more and more complicated, the cost does usually tend to climb. And again, as Alex can attest, what he's going to be talking about, the expense can be fairly high.
Yeah.
And again, it isn't easy. Again, as we're going to talk about in the next slide, there is a lot of work. You're never going to get it right the first time. You're probably going to break things the first times you work on things. On 68K MLA, which is a Macintosh forum, there's a user there in Germany by the name of Boll. He reverse engineers expansion cards for the Macintosh. He very publicly will tell you, I have destroyed examples of these cards that I have found, bought, received, whatever, because my attempts just failed, and it failed catastrophically. So there is a barrier for difficulty that even somebody that is experienced is going to have to overcome, not just as things are scaling up, but sometimes you just run into a problem that is going to seem insurmountable. Talking about what reverse engineering is, it is a very involved process, as everything in the last slide would tend to convey. There's a tremendous amount of work involved. Even when it is easy, you are still having to research, you are having to find documentation for how components work. You are having to find, if it's something very complicated, maybe use cases, maybe published documents that people have written in journals. Maybe you're having to go through JSTOR to find some weird paper that an engineer wrote 30 years ago about how noise affects signal quality on some particular component that just happens to be in the thing that you're working on. It is arduous, might not be the right word, but you're going to have to get your feet into the mud to figure out how these things are working. It's very iterative. So again, as Alex will explain here in a little bit, as you're figuring out how something works, especially in something that's in a closed environment where you aren't necessarily able to determine what something is or how it does what it does. And the thing that Alex is going to be talking about are programmable logic devices. So with programmable logic devices, you, in a lot of cases, aren't going to be able to just dump those like you would an EPROM and see what the contents are. They have what are called security bits. If those are set, the programmable logic devices work in such a way that you can't ask them to read out their contents. And what that means is you have to go and sniff around for what the chip is doing on the bus or whatever it's hooked up to figure out what's going on. And in doing that, you may get 2 or 3 things right the first time around, and on your second pass, you get a couple of other things right, but you've broken something from your first iteration, where you thought you had all of the arrangement figured out. You really didn't. So now you have pass 3 where you come back, you're trying to reprogram that chip in a new way. It fixes all the stuff you broke the first time, and now something else is broken. And you will do that over and over and over again for things that you cannot immediately see into until basically one of 2 things happens. You succeed, or at least you have a stable enough end result that it is not a one-for-one identical clone of the original, but it is a functional equivalent of the original. Or you don't succeed. And as somebody that doesn't succeed from time to time, failure is natural. It's part of this process. Step away, come back later. It is not worth just giving up, but you do need to know that it is not going to be a one-stop shop for whatever it is that you're trying to accomplish. You're going to have to iterate upon your work. A lot, as Alex, again, will explain with some of the practical examples that we've got. As the first two things have demonstrated, it's very time consuming, and it's also probably very money consuming, especially if you were trying to figure out how something that is rare or on its own because of equipment cost is very expensive. And if you want to figure out how that thing works, you're going to have to fork over the dough to acquire that. And if you want to do a good job at it, you're also going to have the tools that are needed, and we'll talk about those here in just a minute as well, that will allow you to be able to peer into how those things work. Lastly, it's difficult. Again, as we've kind of made apparent, it is hard. Even if you were starting with something simple, if the knowledge that you have is simple as well, and there's nothing wrong with that. We all have to start somewhere. Talking about the example with the 555 timer and the blinking LED, if you don't have a grasp of basic electronics, that is going to be difficult for you. But you're going to walk out the other side of figuring that out with a little bit better basic understanding of how electrons flow from one place to another. And in some cases, as you're moving to more and more advanced things, how things like digital logic work. And I'll talk about that again here in just a moment. Why is all of this important? This sounds like an absolute pain in the butt. It sounds expensive. It sounds like there's little payoff. It sounds like you're probably going to just have a real rough time working through it. It is extremely important. As this show can kind of demonstrate, there's a lot of legacy systems out there that are worth keeping alive. Outside of this show, there are people that have to maintain legacy systems because their job requires it. Places like banks still have a lot of their check processing systems that run on COBOL. My boss was a former COBOL developer. That is still a thing that somebody has to go maintain. And if you lose your institutional knowledge and you don't have good enough documentation, somebody's got to come back and figure out how that works. And the bigger the system, the more that's going to cost, obviously. So kind of bringing it back in to look at the things that we work with here, if you wanted things like the Centurion, like you can go watch Usagi Electric's videos on that. He is constantly having to figure out how things work on that machine to keep it running, because there just isn't enough documentation to allow it to be maintained. He was kind of having to figure out some of it as he goes. And if you want to preserve a lot of the history that we work with here, it's going to have to be kind of picked apart and figured out, which kind of bleeds into the next. Ideally, you're doing it while it's still functional. And in the case of where you're not actively trying to maintain something that's running to keep it going, it's also important because you want to document and preserve how things work so that they can be iterated upon again. They can be reproduced. We can just make new hardware. Maybe we don't have the original parts available anymore. They're EOL. They haven't been manufactured in 30 years. That's cool. Can you build something modern that does what the old one does or did? Probably. But you have to know how the old thing did what it did in order to do that with newer hardware. You can't just guess. It's very important if you're trying to fix bugs in unsupported systems, if you're trying to make functional improvements to unsupported systems. A good example of this would be things like ROM hacking in video games. There is a huge community of people that do nothing but sit down and fix old bugs in things like Super Nintendo games or Sega Genesis games, or they retranslate and re-release newer versions of those games because the originals were sometimes borderline unplayable. And that requires you to kind of pry apart that ROM and look at how the game works, look at how text processing is handled, and then put your own content in there, your own code, your own text, and get that to mesh and jive with how the game runs so you don't just crash it. It's also useful and important for things like interoperation. Another example here at the show, AJ at Forgotten Machines has a bunch of terminals that use a proprietary protocol that's entirely undocumented on hardware that's entirely undocumented. If you want to hook those things up to anything else, it's going to be next to impossible to do unless you have that understanding. So That's an example here. If you have a real world example, if you have two systems that you need to be able to talk to each other that do things like hand off data via an API, or you need to build an API for data to move from one system to another, you have to know what you're getting out of the old system to put into the new one. And if there's no documentation available, you're probably going to have to poke and prod at it. And this is more of a talk about hardware rather than software, but there is some software involved. That's more of a software example. But it is entirely relevant. And if you don't know how the thing you're working with works, you're not going to be able to progress. Lastly, it is an excellent way to just further your own understanding of how things like digital logic work, how digital signals work. I've been working with Alex for, a year and a half or two now?
Yeah, something like that.
Something like that, on reverse engineering Lisa hardware, and I knew a little bit going in. I kind of knew I was wading into territory that I was going to be very inexperienced in, and I've come out on the other side having a much, much better understanding of how very intricate digital logic works. And I did not have that before this. I can look at things that Alex is working on, and I've got a much better understanding of it. And that doesn't just apply to this, that applies to problem solving in general, because if you're expanding your horizons about how things work by taking them apart and seeing what they do, and then explaining how those things happen via documentation, building your own examples of them, that is a fantastic way to build your problem solving and analytical skills that helps in everything.
Just FYI, you probably only got about 3 or 4 minutes left before we hit the halfway point. So,
okay. Yeah. So some general examples of reverse engineering in the things that we look at here. The PC BIOS. That was picked apart by Compaq and later Phoenix. And now we have PCs. Like, not IBM PCs, obviously. We have literally everyone that has a computer in this room that is built off that architecture is thanks to those efforts. Computer and video game emulation. Another good example. You have to take those things apart and figure out how they work, and then rebuild them in software, which is not an easy feat. Linux. I don't think I have to say very much about that. Unix-like OS, built from the ground up, had to be picked apart and rebuilt. Retrocomputing. Obviously, if you are an attendee of the show, you have probably interacted with a machine that's running some kind of emulated hard disk or emulated floppy disk, some kind of emulated storage. If you've used any kind of, like Vince Briel's emulated VT100, or just a terminal emulator in general to talk to something over serial, same thing. You have to know how that works. That last one, removal of copy protection, is important because, going back to talking about preserving things, there's a lot of software and a lot of games from the distant past, and still, but primarily retrocomputing we're talking about here, where those games would just be unplayable in a modern context if somebody did not go back and figure out how things like copy protection or licensing, or maybe it required a hardware dongle, went in and figured out how to turn those things off so that other people now, when the media that all that came on was just long gone. So what do you need to do this? And Alex is going to demonstrate some of this as he's talking about the stuff that you're working on. Some of the basic tools that you're going to need to start with are just a soldering iron and a multimeter. The multimeter will let you tone out traces, and a soldering iron will let you reassemble the things that hopefully you might need to take apart. Tools that are nice to have. A desoldering gun. So if you need to take apart a large PCB, if you're doing hardware reverse engineering, and you're okay with doing it in a somewhat destructive fashion, you're going to need one of those, because it is going to take 1,000 times longer otherwise. Cannot praise them enough. Having a digital microscope to look at whatever hardware you're working on, also very convenient, because you don't know where, when you run into a problem, it might be because there is a hairline crack in a trace, and your eyes just can't see that small. And being able to see things at a micro level is incredibly helpful. Some expensive tools, but that are nice to have, which Alex has one here. Digital oscilloscopes have come way down in price. You can get one for a couple $100 now. Same thing with logic analyzers. There's a bit of a learning curve, to using those tools, but they are incredibly valuable, especially when you're doing what Alex is going to be talking about here in a minute with an actual use case scenario. Software. If you're going to be producing a reproduction of whatever it is that you have just picked apart, you're going to have some kind of CAD or EDA utility. I'm sure everyone that has worked with PCB design in here is probably familiar with KiCad as far as open source goes. I misspelled easy, I apologize. Easy EDA is a cloud-only one. They have direct integration with JLC PCB. Eagle, Altium. If you work for a large business, you might be using something like AutoCAD or SolidWorks. Image editing, which Alex will, again, a practical example here in a moment, he'll be covering what he does with that. It is good to be able to review images if you're just going over traces. It's nice to be able to literally cross off the work that you've done. Text editors, some kind of IDE if you're working with microcontrollers, also very good to have. I'm going to try and speed up just a little bit, I'm sorry. So, basic skills that go into actually picking something apart. Soldering and desoldering at the base. So if you're going to be taking something apart, you're probably, if you've never soldered or desoldered anything, you're probably going to suck at it at first. That's okay. Work on scrap. Find just trash PCBs, take things apart. Your skills will improve the more you do it. Basic knowledge to have going into it. Again, basic electronics. And as you work on smaller scale things, you will learn more about how basic electronics work. But it is always good to start by reading up on how electrons get from point A to point B and knowing what to be looking out for while you're doing that, especially with analog components. Having a good knowledge of digital logic, also good. You want to be able to understand the chips you're looking at and what they do. Because that will give you a much better idea of the general function of what you're going to be working on, so that when you're ready to either make improvements or maybe you've run into a bug that you need to address, you have an idea of what components are doing what on that board and where to start looking. So things like you have some kind of bus conflict. Well, it helps to know what a bus transceiver is, and knowing what that is, what the part numbers are, and how it works. Having some basic programming knowledge, also very valuable. If you're going to be working with microcontrollers, being able to even do something as simple as turn an LED on or off. That's input. That's input to a system or output from a system. How to read schematics, also very valuable. Again, as you work with small electronics projects, that allows you to kind of grow your knowledge of how designs are printed in a schematic and what does what. Safety is also another important thing, not just for you, because if you're going to be eventually working with something like high voltage, don't hurt yourself. But also, you want to take precautions to make sure that you are not going to damage the thing that you're working on, especially if, as Alex is going to show here in a minute, it's something expensive. You want to take precautions to make sure that static electricity is not potentially going to damage that. Some of the more advanced skills to work with are things like how to use those EDA tools to the extent that you should be using them, especially if you're going to be working with large or complicated multi-layer designs in a circuit board, if you're working with hardware. Again, working with microcontrollers, start small. Blinking LED, that eventually grows into larger things that, and again, you can demonstrate here in a moment with the hard disk emulator that you have, that runs off an ESP32 microcontroller. And that's it. There's very, very little to it other than the code to make the microcontroller do what it needs to do. Knowing how computers work at a base level is also very important. If you're going to be working on something like the Lisa, you want to know how all of the different bits of the computer communicate with each other. You also want to try and diversify your knowledge of programming languages beyond just picking up C++ or Python. Each programming language brings to the table a different set of things it will let you do, especially if you're interacting with microcontrollers or if you need to work with the systems themselves. And lastly, as you use tools, you will get better at using tools. Hammers do one thing, oscilloscopes do many things. You don't have to work very long with a hammer to know how to use it. Knowing how to use an oscilloscope takes a little bit of time and patience and use to get to the point that you know what you're looking at. Same thing with a logic analyzer. So now I'm going to hand off to Alex, and he's actually going to walk through a practical instance of what goes into reverse engineering a piece of hardware and how insane it can get. Not necessarily how it will always be, but how deep the rabbit hole can go. So I'm going to hand that over to you.
All right, let's make sure our cables don't get crossed like last time.
Yep.
Okay. So before we actually start talking about the particular piece of hardware that is going to be our example for today, I did want to talk about GALs, which are these particular types of chips that are going to be very important for this particular piece of hardware. So a GAL, it stands for generic array logic, and you can basically think of it, if you know what an FPGA is, it's basically a really tiny scaled down FPGA. It's a chip that contains an array of AND and OR gates, as well as some registers. And you can wire these AND and OR gates together in whatever configuration you would like. Well, with a big asterisk after that, but in whatever configuration you would like in order to execute whatever logic operation you would like it to. And then at the end of that logic operation, you can attach, if you would like, you can attach a register to the end of that to provide a little bit of state to whatever that operation may be. And these are very limited devices in that you only have a set number of product terms, meaning a set number of terms separated by an OR. So in a GAL 16V8, which is the device that we're going to be talking about here, you only have 8 product terms available per output on the chip. So that ends up becoming very limiting when you're actually writing equations for them, which can be both a good thing and a bad thing when you're actually reverse engineering them. So we will talk about that a little bit later. And the main purpose of a GAL is to consolidate logic that would previously be discrete, meaning just TTL logic chips, like 74 series logic chips. You can consolidate all of that into a single chip using a GAL, which simplifies your circuit board design and often makes it cheaper and harder to copy as well, which we're about to get into here. GALs are very hard to reverse engineer a lot of times because they have a security fuse in them that prevents you from reading out their contents. Because in order to program a GAL, you just put it into a PLD programmer such as the T48 right here. I'm sure some of you might be familiar with this. You just program the GAL in this using plenty of pieces of software that are available. But after the GAL is programmed, the software will set what's called a security fuse. And this fuse prevents you from being able to read what was programmed into the GAL back out after it has been programmed. So this basically prevents other people from copying whatever design you programmed into it. So this is great for the designer because, you know, you can't infringe upon their design, but it's really bad for a reverse engineer because it makes it really hard for us to actually replicate this design. And it is possible to actually bypass the security. If you provide the right voltages to the right pins on the GAL at the exact right times as you're powering it up, you can actually glitch that security fuse and get past it and read the contents out anyway. But that only works for certain types of GALs. And it's also rather dangerous because if you do it wrong, you can actually just fry the chip. And if it's a really rare chip, you don't want to do that. So, you know, that's only for like really extreme cases. And that's no fun anyway, because you don't get to actually reverse engineer it yourself. It's kind of cheating in my opinion. So I avoid that when I can. So the only other option when you don't want to do that is actually just looking at all the inputs to the GAL and looking at all the outputs that are coming out of the GAL and determining the relationship between those inputs and those outputs. And that can be a real challenge sometimes, which we will get into here in a second. So now that we've talked a little bit about GALs, let's get into the actual full reverse engineering example for the day. So this example is going to be the 16 megahertz accelerator here, which is this circuit board here. This is a board that I'm sure a lot of you probably have not heard of before because it's very obscure. This is a board for the Apple Lisa computer that accelerates its processor from the stock 5 megahertz up to 16 megahertz. It only works when the Lisa is running Mac OS, but still, it's pretty impressive. And it also optionally adds SCSI support to the Lisa so that you can connect a SCSI hard drive. There's also an optional FPU socket as well, so you can add like a Motorola 68881 or 882 FPU. And it also adds RAM that is faster than the Lisa's built-in stock RAM, and that's what these SIM sockets are for right here. And in its stock configuration, the accelerator supports up to 4 megs of additional RAM, and then in its upgraded configuration, which is the one I reverse engineered, you can actually add up to 12 megs of additional RAM to your Lisa, which is pretty crazy. And this is an original accelerator right here in my hand, but that picture right there, that is my replica accelerator. And just a disclaimer throughout this entire process, everything I'm explaining here, the company that developed the accelerator and the individual who basically designed the entire thing, Sigma 7 Systems, they still retain the rights to this design. So even though I reverse engineered it, I'm only going to be able to provide a limited amount of info here because they've asked me not to share too much about it, and I want to respect that. So yeah. So starting off with the easy part of things, at least relative to the gals, the easy part is the actual circuit board itself. So the way that I did this in this case is I depopulated all the components from the board. So I did that with the desoldering gun that we talked about earlier. It took absolutely forever, but I removed every single component from the entire board. And that left me with just a bare circuit board, which I then put on the scanner, and I took some nice high-res 1200 DPI scans of both the front and the back of the board. And once I had done that, I opened up my schematic software. I use Easy EDA just for the nice integration with JLC PCB and all that. And so I opened up my software there, and I just started following every single trace on the circuit board to figure out where it went. And each time I would follow a trace from start to finish. As you can see on the side of the slide there, you can see each time I would follow a trace, I would mark over it with red ink. I had it open in, if you're familiar with Mac, I had it open in Preview, and I would just draw over it with ink each time I would follow a trace so that I could know which ones I had followed and which ones I hadn't. And it's also possible, of course, as Will mentioned earlier, to just probe each trace with a multimeter to figure out where they go. But I wanted the trace layout when I made the actual PCB design. I wanted the layout to perfectly match the original just for maximum authenticity. So, and the only way to do that is to completely depopulate it so you can see exactly where all the wires go underneath the components. So that's kind of why I opted to do it the way that I did, right? And as you start doing a schematic like this, it can start out really confusing because when you're tracing out the first few wires, like you really have no idea what they're doing. Like they're going from one component to another, but you may not have any clue what their purpose is because you just have a couple of them and you have no context for what they're doing in the grand scheme of things. But as you start to trace out more and more of them, you'll start to get a better understanding of what they're actually doing as things start to interconnect with other things. And then you can start naming the signals on your schematic a little bit better, and you can start getting a better understanding of how things are actually working, which is really nice. And once we have the schematic fully created, now we just need to design a replica circuit board because the schematic's only half of it. We actually need to make a board layout of things. And the way that I normally do this, because I just like maximum authenticity to the original for the most part, I normally just replicate the original design as close as possible. So I use those scans and just follow them as closely as possible when routing traces and placing components on my replica board. And that picture up there is a little segment of my replica accelerator PCB in the design software. But you can also make changes if you'd like. And there is one change that I made to the accelerator board. The original on the SCSI connector, it didn't actually supply termination power to the SCSI connector. So you can't connect something like a blue SCSI and just have the blue SCSI be powered straight off the SCSI connector. And I didn't like that. So obviously that's a very simple change. It's just adding a diode, but it is a change nonetheless. So that's like one little change that I made to this board. I made bigger changes to other boards, but that's just an example here. And generally, even if you do make changes, it's generally a good idea to keep your design somewhat similar, at least to the original board, particularly in terms of the layout, just for signal integrity reasons, because if you make it too incredibly different, you might start having issues with noise between different signals, or if your design is really timing sensitive, a trace being longer than it was on the original could actually throw off the timing, although that's not really an issue on things like this. So it's generally a decent idea to keep things fairly close to the original in terms of layout. But now that we have the board figured out, now it's generally a good idea to just study the schematics some and figure out what things are actually doing. This isn't necessary. Like if you don't care and you just want a replica board, you don't have to do this. But it's fun, and if the design involves gals, it's actually often pretty darn necessary to actually look into the design and just figure out what things are actually doing so that you have context when you're trying to figure out what the gals are doing. So on this slide, I just want to talk a little bit about how the accelerator actually works, because I think it's just a really interesting design. So there are 4 main gals on the accelerator: U4, U5, U6, and U11. So when you see those mentioned up there, that's what those are. So U4, just to be clear, with all this description, I haven't actually reverse engineered the gals yet like I have in real life, but just looking at this, you don't need to know what the gals actually do internally to understand this stuff. So just looking at the schematic, you can figure all this out, is what I'm trying to say. So looking at the schematic, you can see that U4 handles basically just glue logic. So chip selection for the FPU and the SCSI chip, that sort of stuff. No particular function. It just does kind of a bunch of random glue logic. Then the U5 gal mainly handles refresh for the DRAM sims up here, because it is dynamic RAM, so the memory does need to be refreshed periodically. And it also handles inserting wait states for the RAM, because this board supports both 0 and 1 wait state memory. So it can also, that chip also inserts wait states when necessary for the RAM. And then there's also a 555 timer and a binary counter that connect to U5 to handle the timing of the refresh. So that 555 timer will go off every several microseconds, and that will tell U5 that it's time to refresh part of DRAM. And then it will refresh, it'll trigger the counter to refresh a few addresses of DRAM, and then the U5 will re-trigger the 555 timer again, a little bit of time will pass, and then we will refresh a few more addresses. And the counter is just counting up through memory addresses to refresh different parts of DRAM each time we enter a refresh cycle. And sorry, I wish I could explain all this in more detail, because I think it's all really cool, but we don't have a lot of time, so I've got to go through it just fairly quickly. So sorry if the explanation doesn't make a lot of sense. And it's also fun to experiment with stuff when you're going through and learning about this stuff. So one thing, when I learned that the 555 timer controls refresh, I decided to try increasing the capacitor value connected to the 555 timer to see what would happen if I increased the refresh delay, to see what would happen if it refreshed less frequently. And well, sure enough, my RAM was okay with that. And well, increasing that delay actually improved performance fairly significantly, because we weren't wasting as much CPU time just waiting for memory to be refreshed. So it's fun to just do little experiments like that too as you figure stuff out. And then there are also some multiplexers on the board that select between whether or not we want to address the RAM via that counter when we're refreshing things, or address it via the CPU when we're just doing normal memory accesses. And then the U6 gal, it controls the actual addressing of the RAM using like the RAS and CAS signals, as well as the selection of the multiplexer. So the signals that actually flip the multiplexers back and forth between refresh and standard RAM addressing, that is controlled by U6. Then we also have an MCM 2018 SRAM chip on here, which I originally thought was being used as like cache, but after a little more investigation, I now think, just to be clear, this is still a theory, I can't be 100% sure, but now I think it's being used as a state machine for basically just sequencing operations on the rest of the board. So there are a couple outputs of that RAM that are hooked to some of the gals, and the gals perform certain operations when those outputs go high or low. So it seems like a state machine that is loaded by the driver that drives the accelerator at boot time, and then that is what actually turns the accelerator on, makes it start speeding the computer up. And the fact that it's software controllable would also allow you to alter the behavior of the accelerator in software, maybe fix bugs and do things like that, which is kind of cool too. And then the U11 gal mainly handles address decoding pretty straightforward, but also licensing, because there are 3 different versions of the accelerator. One just supports the main processor speedup functionality. One supports processor speedup and the SCSI port. And the 3rd version supports processor speedup, SCSI port, and FPU. And the license gal that determines which version you have is U11. And the only difference between those 3 accelerators is which version of U11 you have. So just by popping out U11 and popping in a different version of U11, you can unlock those extra features. So it handles that by basically just disabling certain outputs to prevent the SCSI chip or the FPU from even being selected to begin with. And that's how it does that. And there's also a RAM mod gal, which piggybacks on top of one of the multiplexers. And that's an optional upgrade, but that allows you to have 12 megs of RAM on here instead of 4. And that just basically adds an extra address line to the SIM slots. And that's how you get extra RAM on your accelerator. That's pretty simple, right? And another interesting thing I learned is the accelerator actually runs at 16 megahertz all the time, even when turned off. And the gals just insert wait states, like on the DTAC line that is part of the 68,000 processor that acknowledges data transmissions to the rest of the system in order to make the rest of the Lisa think that it's running at 5 megahertz when turned off. And then DTAC basically just speeds up when the accelerator is turned on. So it's a very interesting method of doing that, but it actually won't work with the Lisa Office system, which is LOS, because the timing of those wait states that it inserts aren't quite perfect. So kind of an interesting thing there. So that's the kind of stuff you can learn when you actually study the schematic, and all that really comes in handy when you're actually reverse engineering the gals. So to do that, you just connect a logic analyzer, which I did not bring, but that is the logic analyzer I use, the LA2016. It's a little USB-based analyzer. You connect that to each gal with a little chip clip, and you just figure out the timing relationships between the inputs of the gal and the outputs of the gal. And this can be tough because some outputs are purely combinational. It's just combinational logic, which is rather straightforward. But then some outputs, there's also some state involved. So the current state of the output influences what the next state of the output will be. So that makes things a lot more challenging to figure out a lot of times. And another problem that was actually a bit of a bigger problem for me during the reverse engineering process was that thing I talked about earlier, where the GAL16V8 devices only allow you to have 8 product terms per output. And that was a massive challenge for me, because after enough studying, I could pretty much always figure out a logic equation that would work for each output. But pretty much every time, the equation was way bigger than 8 product terms. And so I would sit there for like hours and hours trying to condense the darn thing to compile down to less than 8 product terms. And it was a massive pain. And then one other thing that you have to keep in mind too, just capturing one logic analyzer trace and then staring at it and looking at the timing relationships for the signal in a couple places, that isn't enough, because there are always edge cases. There are always some weird edge cases somewhere that you're not seeing, and those will always throw things off. So you think you have it, you write the equations, you try it out, it doesn't work. So then you take another trace at the point where it doesn't work, and oh, now I found some new case where the signal behaves completely differently in some new context that I didn't even see before. So now I've got to add more stuff to the equation to account for that. So that's one of the big challenges with reverse engineering these things. So here's a very simple example from the accelerator. This is just one of the like maybe 30-something equations I had to write from it. This is an incredibly simple example. But this is the equation that I wrote for the chip select SCSI signal, which is this signal here, the blue one. So this equation basically says that chip select goes low when the Gal Connect 3 signal is low, which is the yellow one up there, and the address strobe accelerator signal is low, which is the green one up there, and the A9 signal, which is the purple one right here, is low. And we can kind of see that here. A9 is low here, Gal Connect 3 is low, and address strobe accelerator is also low. And when all those conditions are met, chip select also goes low. And you might be wondering, okay, well, how do you know that A9 has to be low in order for this to go low? Because all the cases where those two meet the conditions, A9 is already low, so you don't really know that for sure. Well, the way that you know that is because if I were to zoom out on this trace here, you would find other examples of where both of those signals are low, but A9 is high and chip select doesn't go low. So there's a lot of like just analyzing every single case where something occurs in order to make sure that you are indeed tracking the very signals that are causing that change in state. Because sometimes it looks like you are following the signals that are actually causing the state to change, when in reality it's just a red herring, and that signal just so happens to be changing state at the same time as the one that you're tracking. But occasionally it doesn't, and you actually should be basing it on another signal instead. So it can get very convoluted. This is a super simple example. And this next slide, I'm not going to explain how this next one works because it's super convoluted, but this next one shows a more typical example because this is probably the second most simple out of all of the ones for the accelerator. This next slide, that is what a lot of them look a little bit more like. That is the equation for this guy right here. I'm not going to explain that, but yeah, they get crazy.
Something to interject with. The amount of bandwidth consumed by performing a trace of sufficient length to be able to determine this is gigabytes in size.
Yes.
For mere ones of seconds
Yes.
of data. It is, what, 6, 7, 8?
In other words,
Do what?
we need modern equipment to figure out.
Yes.
Yes.
Yeah, I think I've got like 72 gigabytes worth of logic analyzer traces from this accelerator project in total, which is crazy. And so once you think you figured out the gals, now you can move on to testing stuff. So one thing that I screwed up on when I first did this was when I was designing the board. The original board is actually a 4-layer board with signals on the outer 2 layers and power and ground on the inside. But I opted for a 2-layer design because I'm cheap. I'm a college student. I don't have a lot of money, so I wanted to go for a cheaper 2-layer board when I did that. So that's what I did the first time around, but unfortunately it didn't work because, well, signal integrity issues. There was too much noise on a couple of the signal lines because we didn't have those big, awesome planes in the middle.
Like
and
4 megahertz, maybe 10 megahertz.
Exactly. And 16 megahertz, heck no. So yeah, that just didn't work. So I unfortunately had to redesign the board 4-layer, and luckily the board worked that time. But at that point, I was just using the original gals from the original accelerator in that board just to make sure the board worked. So then I moved on to the gals, and as it says there, they took hundreds of attempts, and I'd say over 1,000 hours. I don't know how many hours, but a lot of hours to get right. It took
At least they're erasable.
freaking forever. What?
At least they're erasable.
Yes, at least they're erasable. Although
Yeah.
I erased a couple of them so many times that they actually died, and I had to get more. So yeah, I erased them so many times. It was crazy. But yeah, one thing here, do not try doing, if you have a bunch of gals you have to do, don't try writing equations for them all and popping them all in and testing it like that all at once. Don't do that. Do one gal at a time. Have all the original gals in, pop one of the originals out, and put your replica gal in place of that one original one, and get that one working solidly before you move on to any of the others, because there is no way you will ever get it working if you try them all at once. Do not do that. And then once you do get it working, make sure to do a lot of exhaustive testing before you actually claim success. Because there you will find bugs. I was like, oh my god, I finally got this thing working. Oh my god, this is so cool. And then I inserted a floppy disk and got a system error. So, and then I did a little bit of probing around and figured out what was wrong there, fixed that, and then got another address error a few minutes later. And did some more probing around, fixed that, got some more errors, and then finally, about a week later, I was able to fix all the stability errors, and it was finally rock solid. So make sure to do a lot of testing before actually claiming victory, because there are going to be problems, even if you think it is working perfectly. And one final little ethical thing to talk about a little bit, about intellectual property with all this stuff. It's very controversial about, protecting the IP of the original designers, especially if there are gals involved. Like, how does this work exactly? If you've put in all the effort to replicate a design yourself, do you have the right to share it online? Do you have the right to share it publicly? If you haven't used any of the original files, original source code, if you haven't used any of that, do you have the right to share your design publicly? That's a big question, and
especially if the original designer is not alive anymore.
yeah, and in that case, I would be inclined to say yes, absolutely. I mean, they're not around; who cares?
Yeah.
But in the case where they are still alive and they actually still claim the design, then there's more gray area there, and it's kind of
The real
tough.
question is,
And
there's two ways they could say it's like, oh wow, somebody cares, and the other is, no, you can't have it, you can't, it's money, So
exactly, there are two sides there.
Realize it's not worth anything anymore.
And in this case, the designer has asked that I keep this private because he says there's a chance that he might try selling these again at some point in the future. So he has asked that I keep.
Middle road there.
Yeah. So he has asked that I keep all this private, but he has said that given that I have reverse engineered all this stuff, he said that he might allow me to sell people pre-programmed gals and bare PCBs as long as I give him a royalty. So I wouldn't be charging I would just be charging people for the parts and charging them the royalty and then giving it to him. I wouldn't be asking for any money myself because I want to make this open source. But at least that's a compromise, right? Because these things they sell for over $1,000 when they pop up on eBay once every couple years. So people being able to buy gals for, I don't know how much you would want for royalties, but people being able to buy gals for hopefully less than $150, I don't know, is way better than paying over $1,000 on eBay.
The couple of grand they're slowly inching towards.
Yeah. So I'd say that's definitely a good compromise for now. Yeah. So yeah, that's a little thing I wanted to throw in there at the end. And with all that out of the way, does anybody have any questions about any of this stuff?
I have one.
Yeah.
But it's kind of like 3 questions in one subject. So the first off is, so why do you depopulate the components if you can still trace it, within it? Second part is, does marking trace works in multi-layer boards as well? If not, how you can find the remaining trace? And the last one is, what type of scanner did you use to scan the boards?
Okay, I'll start with the last one because that one's really easy. It's just like an HP color laser jet, whatever. It's just a regular old. It's nothing fancy.
Yeah, the one that I use is care of Dallas Makerspace. They have a high DPI scanner. So
and the one I use is just a laser jet I have at home. So, yeah, it's nothing special, but it gets the job done. It's plenty high res for what I got to do, so whatever. In terms of multi-layer boards with actual traces on the inside instead of just powering ground planes, luckily I haven't had to deal with one of those yet. But no, obviously they are a lot more complicated because you can't really see what's going on inside. So you have to use a lot more mental power for those, because instead of just blindly probing traces or just following traces to see where they go, you actually have to use inductive and deductive reasoning to figure out, okay, well, I've got something that starts here and goes somewhere. Where do I think this could possibly go, logically speaking, in order to make this board do what it's supposed to, right? And then you can use a multimeter to confirm that, right? You can probe around and see if those 2 points are connected like you would expect. But that of course gets a whole lot more difficult when you're doing it. You could do that, although yes. I don't have any equipment for that. So
now there is
a friend who works at a clinic or something, or
yeah, that would work. I didn't even mention that because I don't know anybody who has the equipment, and I figure most people don't. So
nowadays they're using USB-based images even. So.
Yeah, sure. If you got an X-ray machine, go for it. That works.
So there is actually a middle ground between X-raying and probing out that. It is unfortunately completely destructive. You never see it used with stuff like this. You see it used on things that, oh, hey, I can just get one of those for $20 on eBay. And that is, if you have, generally speaking, if you have a 4-layer board on something this old, it's going to be power and ground rails that are in the middle.
Yeah.
If you have newer things that are 4-layer, or 6-layer, or 8-layer, or God forbid, the newer 12 and 14 and 16-layer manufacturing processes that are starting to come out, you basically have to take the circuit board and sand off each layer. And you were talking about literally either hand sanding or putting it, as some of the guys that have reverse engineered Macintosh like LC and Classic logic boards. They literally took a belt sander, held the boards down, sanded the layer of fiberglass off until they got to the interior copper layer, finished it by hand, scanned it, put it back on the belt sander, took the next layer of fiberglass down until they got to the second inner layer, scanned that, and you know what the front and back look like. And then you work with that. And yes, it is destructive in the most literal sense. You are going to throw that away when you're done with it. It's completely
Breathing protection.
Yeah.
Yes. Also, if anyone does want to try that, one, don't. That's a mess. Second, absolutely wear breathing protection. You will be otherwise inhaling fiberglass. And take it from somebody who's had relatives that have dealt with COPD and mesothelioma. You do not want that.
I hate to even think about those destructive methods. Oh, you had one
Yes.
more question, right?
Yeah, why did you depopulate the component instead of just leaving it in and then do the tracing?
Yeah, so two main reasons. One, it's just a little easier to follow the trace. Well, I guess three main reasons. One, that can make it a little bit easier to follow the traces. It is a pain to desolder everything, but
Yeah.
I didn't mind and whatever, right? Like I find it kind of fun actually, so whatever. Two, I wanted to just have scans of both sides of the board just for like archival preservation purposes because I mean, these are very uncommon. Nobody has that yet. So let's depopulate it for the sake of scanning it, right? And three, when I replicate things, I like making things that are very authentic to the original. And so I wanted the trace routing to be very similar to that of the original. And well, when you see a trace disappear underneath a component, the only way to see where it goes is to remove the component, right?
You also
So
do it right if you've got the traces near following them too.
Yes.
You know you've done it right when you.
yes,
Yes.
that too. That's another great reason. That is another excellent reason. So hope that answers your question.
I was just curious what part of the overall process brought you the most joy? Which one, what step tickled the nerd brain the most?
Well, finally getting the darn thing working after the PCB part was easy by comparison. The gals were what took me several months. Not like I was doing school, so like not just like 24/7 work, but it took several months on and off to do. So finally getting those done was the best part of the process. But I'd say the most satisfying like yes moment was probably getting U5 working because that chip was just like that long equation I showed. U5 was pretty much nothing but those long equations. And so I'd say getting U5 in particular working was probably the most exciting moment. But
Registered ones to deal with? I mean, were the registered pins outputs to deal with?
that one I showed actually, the really long one, that one was registered.
Okay.
And yeah, most of them were registered. There were a couple that weren't, but most of them were registered.
That's when
So
it gets hard to-
that is when it gets very hard. Yeah. So
But real quick. So this was one that I worked on, which was the CPU card out of the Lisa. All said and done, this was about 3 or 4 months worth of work. The part that tickled my brain the most was when my wife asked me, "Are you done working on that?" And I said yes, and she sighed and said, "Oh, thank God." So, yeah, it's in all seriousness, but slotting this in and it not having any problems. It does what you expect it to do. There is such immense satisfaction that comes out of that. It's like building a ship in a bottle. I mean, it is intricate and complex, and when it works, you just want to jump for joy.
yeah.
Yes.
So I know you had previously mentioned how today the PC as we know it, we might not have it if Compaq, these other companies hadn't reverse engineered the BIOS and the hardware that went into the actual PC to build these clones that built that market. I was going to ask, what potential qualms do you have with releasing reverse engineered hardware? It's unsupported relatively. It's any patent on it might be way expired. If you're using your own code on it and someone says, well, I might make it, in the tech community, we received a lot of mites that never came about, and then things, just went the wayside. So what potential qualms do you have in that situation?
So yeah, so if the person who created it is dead or doesn't care, then obviously, whatever, I will put it out there. I do not care one bit. If the person does lay claim to it and actually does care about their intellectual property, then in that case, it's definitely more difficult. But I do want to kind of respect what he's doing here, because he did put a lot of effort into designing this thing. Like, the design is really, really clever, and he did put a lot of effort into designing it. And he's also like he's a very prominent figure in the Lisa community, and he's very knowledgeable. I really respect that, and so I kind of just want to respect everything that he did here, because I really respect his knowledge and acumen when it comes to this stuff. So definitely case by case basis, right? But here, that's kind of how I feel in this particular context.
I'd like to make a little bit of a counterpoint to that, being that I feel honestly that a lot of people, like you said, he might consider in the future doing his own, and that is one of the reasons. But when I like to do something and show respect, I'd like to get that out to as many people as possible. Like, hey, look at this great work that this person did. I believe it's okay to raise awareness of the originator of that. Send this person a little bit of love. But before today, I hadn't known about this, so it's you that brought this to my attention, and your efforts that brought his work to the attention of a wider audience.
That's another way of thinking about it. Absolutely, kind of like free marketing, sort of. Yeah, that is definitely another way of thinking about it. Yeah.
Oh, we're at time. Okay.
Okay.
That.
Yeah. Thank you, everybody, for coming today.
Yeah. Thank you.